Hi, I'm an old guy and I do maths. Today we're looking at the unattractive subject, or the unattractive sounding subject of decay. Those of you who do physics or chemistry will recognize this. Those of you who have done financial maths may well have a nodding acquaintance with one or other of the formulas that you see on the page here, but you may know this as a reducing balance depreciation model. Anyway, we're dealing with decay because we're dealing with, in the question that I'm addressing, a population decline. Now, the general formula for this is A equals PR to the N, where R is 1 minus little r, which is the rate of decline over 100. And in order for this to be a model for decay, R must be less than 1. If R is equal to 1, we have an equilibrium. If R is greater than 1, we have growth, not decay. So basically R is this part of this formula all wrapped up into one neat number. So let's just define everything. A is the result we're either looking for or the result we have, but it is the end product of the calculation. P is the principal if we're dealing with money, or the initial value if we're dealing with something else. R I've already explained. It is 1 minus the rate of decay over 100. And N is the number of periods that it takes for this to occur. And specifically in this case, because this is in the logarithms playlist, what we're looking at is we're looking at how we find N. So we are trying to solve for an exponential, and that means logarithms. Okay, let's look at the problem. So here's the problem. A species of fish is dying out. It will be listed as endangered when 1,000 fish remain. Currently there are 15,000. The population drops by 20% per annum, and the question is how long before this species is endangered, i.e. how long is it before it moves from 15,000 to 1,000. So I've set this up and I'll just talk through this. So this is the outcome. This is the starting point. 20% is the rate of drop. So 1 minus 20 over 100 to the power of n. Now 1 minus 20 over 100 gives us 0.8. Now that 0.8 is the capital R that I referred to earlier. So our equation is 1,000 is equal to 15,000 times 0.8 to the n. And we can rearrange this as best we can to get this as isolated as possible. What we're actually going after is n, but this is the best we can do with a little bit of algebra. Okay, so 1,000 over 15,000 equals 0.8 to the n. Right, page 2. 1,000 over 15,000 breaks down to 1 over 15. So 1/15 is equal to 0.8 to the power of n. How do we go about this? Well, the clue is here. We take the log of each side, and what I've got going on here is I'm just going to do this calculation once I set it up. I'm going to do it using logs in base 10 and natural logs, just to show that they both get the same result, which I'm not sure, in terms of my viewers, who's more used to this or more used to this. Anyway, both work. So here goes. We'll take the log of both sides, but before we do that, we'll just rearrange this. 0.8n is equal to 1/15th. We'll work in this form. You'll see why in a minute. Okay, log, we'll do this in 10 up here. 8.8 rather to the n is equal to log 10 1/15. Okay, now there's one more thing to do. We can use a log rule to get this n out of the way and get it in front of this. So we can rewrite this as n log 10, not log n, log 10 of 0.8 is equal to log 10 1/15. We're very nearly there. So with a little bit more work, we get n is equal to log 10 1/15 over log 10 of 0.8. Okay, so it is now just a matter of going through the motions with this. Now I'm going to do this first, and then I'm going to do it using natural logarithms. Okay, so what have we got? We've got log 1 divided by 15. That's how you enter 1/15th. And we're dividing that by log of 0.8. So there it is in the calculator in logs and base 10. And our answer is 12.1359. 12.1359. That's using logs in base 10. Now I'm going to do it with a natural logarithm, just so you can see this. So log 1 divided by 15, very, very similar input, divided by log 0.8, push go, should get the same number. 12.1359. Now, what does this mean? Well, what it means is that our fish is going to be listed as endangered after 12.1359 years, just over 12 years. So just here, I'll pop this into the equation. So 15,000 times 0.8 to the power of 12.1359. So I hope you can see that. There's our starting value. There's the rate of decay, 0.8, and there is the number of years. So here goes. 15,000 times 0.8 to the power of 12.1359. There it all is. Let's see what we get. Really, really close to 1,000. I'd say it's 1,000 fish and a scale. I think that's a good result. And that is how all this works. Now you can use this for populations, you can use it for nuclear decay, you can use it in chemistry, physics, wherever you're dealing with decay. You can use it in finance, and you only use the logs when you're having to find, when you're having to solve for an exponent, when you're trying to solve an exponential. If you're looking for one of the other numbers, then you don't need logs. Right, well, thank you for watching. I hope you found this interesting and useful, and I'll see you next time. Bye.